All right, so here we go with chapter 7, which is titled Two Strong Acids. This can also be done as if they were two strong bases. You can probably tell by my example that HCl and HNO3 are both acids. So I'm doing this problem as if it were two strong acids, but if there were bases in there like sodium hydroxide and potassium hydroxide, the approach and concept would be similar. Okay, so identify major species. Here we go. We start them all off the same. Obviously, we've got HCl in there, and we've got HNO3 in there. They're mixing them together. Now, what is HCl? It's a strong acid. What is HNO3? It's a strong acid. That is half of the journey. What does that mean, strong acid? Well, what that means is HCl is going to 100% ionize into H plus and Cl minus. That also means that HNO3, because it's a strong acid, will also 100% ionize into H plus and NO3 minus. Okay, now two acids mixing together does nothing in terms of a chemical reaction. There's no chemical reaction going on. However, when you mix them together, it looks like there will be some sort of dilution. You're taking 50 milliliters of stuff and mixing it with 150 milliliters of stuff. So that's a volume change. A volume change will cause dilution no matter what. All right, so we need to go ahead and do the dilution. Now, you have two different acids in there. So you have to do the dilution for HCl, and then you have to do it again separately for HNO3. So what is dilution? M1V1, M1V1, M2V2. Okay, so I'm going to do this for HCl first. All right, HCl. What is the molarity of HCl? It is 0.20. What is the volume? 50 milliliters. Okay, we want to know X, what the new molarity is, M2. And what is the final volume? Well, the final volume should be 150 plus 50 because they're being mixed together. So the final volume should be 200. Okay, so you take and you divide both sides by 200, and the molarity, let's see, I put it in my calculator, and I've got the molarity to be 0.050 molar HCl. Okay? All right, now you need to do this again, but you do it for HNO3. So let's see, the molarity of HNO3 was 0.6. Okay, the volume of the HNO3 used was 150 milliliters. We want to know what its new molarity after the two have been mixed together, and your final volume is 200 milliliters. So after dilution, the HNO3, so calculate this out, I got 0.45 molar HNO3. Okay, so we've got these two numbers, okay? Next thing we do often in this chapter, we haven't done it yet, but we do often, is determine the equilibrium expression. Well, not this time, because this is not equilibrium. These are strong acids. They do not go to equilibrium, so we won't do any sort of equilibrium expression, okay? What we are going to do, however, excuse me while I switch slides. Is we are going to take the long way to solve. So look at, if we said on the last slide that HCl is 0.050 molar, actually I'm going to draw an arrow. What that means is it is 0.050 molar hydrogen and 0.050 molar, sorry I forgot the M's, Cl minus. Okay, so look. I just got the Cl minus. Okay? And then for the HNO3, we said its concentration was 0.45 molar. So what does that mean? It's not really 0.45 molar of this, it's really 0.45 molar of the hydrogen ion and 0.45 molar of the nitrate ion. So look, we just got the molarity of the nitrate ion. So chloride ion concentration, 0.050 molar. Nitrate ion concentration, 0.45 molar. Okay? What about these H pluses? There are two sources of hydrogen ions when they're both strong acids. They both contribute. So the total hydrogen ion concentration is the sum of both of those numbers. This much is coming from HCl, this much is coming from HNO3, so the sum of that is 0.50 molar hydrogen ion coming from the combination of both of those present in solution. So there's our hydrogen ion concentration. Now, how much HNO3 should you have? You shouldn't have any. It's strong. It 100% dissociates. You should only have ion form. How much HCl should you have? You shouldn't have any. It 100% dissociates because it's strong. Okay? All right. At this point, you have many different routes to go to get OH minus, pH, and POH. There's multiple routes. It does not matter the order that you go in. So the first thing I'm going to do is, let's see. I'm going to solve for pH. Okay? I have H plus, so I can find pH. pH is opposite the log of H. Right? So it's opposite the log of 0.50. So pH of this solution ends up being, I put this in my calculator and I got, what are my sig figs? Let's see. These are 2-digit, that's a 2-digit number. Let's pretend that was 0.200, okay? I want this to be a 3-digit number, so 0.301, okay? So then POH is easy. What's the POH? Well, pH plus POH is 14. So if you take 14 and you subtract 0.301, you get 13.699. So up here I just got pH and I got POH. So the only thing I'm missing is OH minus. Again, there's a couple different routes you can take. This is the one I'm going to take. Don't forget about this equation. H plus concentration times OH minus concentration equals 1.0 times 10 to the negative 14th. Oops, I forgot the one. Okay, so my H plus concentration is Actually, I can go back and erase. My H plus concentration is 0.50 times hydroxide. Okay, this is basic algebra. Rearrange, and it looks like if you divide both sides by 0.5, your hydroxide concentration should come out to be 2.00 times 10 to the negative 14th molar. This should make sense. Hydroxides represent bases, right? So this is a tiny concentration for a base, which is good because what we have in here are two acids. So you should not have a lot of hydroxide ion concentration in a solution made up of two different acids. So this should be logical to you. Okay? So the main point of this slide is that if you have two strong acids, or two strong bases for that matter, that the sum of their ions are what determine pH and so forth. So both combined contribute to the total hydrogen ion concentration. If this was a base, it would be both of the hydroxides combined that would be contributing to the hydroxide concentration. Okay, so that is it for chapter 7.